All right, let's take a look at 7.8 and finish up our discussion of Chapter 7, all about integration techniques. So the topic of discussion in 7.8 is improper integrals. And there are two types of improper integrals that we need to consider, right? So first of all, you may recall from your Calculus 1 days that it's assumed that in the definition of this integral from a to b of f of x dx, that a and b are finite numbers. But in fact, it is possible for us to consider cases when b is positive infinity or a is negative infinity or potentially both. In certain cases, that's not a very interesting thing, right? So if you're looking at like x squared or something, and you're trying to integrate from 3 to positive infinity, well, obviously that area is just going to be like a really big number. It's going to be an infinite number, so that's not interesting. But take a look at this. If you have this kind of situation and you're interested in integrating from 3 to positive infinity, it's possible that because this thing is decreasing, that you could get some kind of finite value out of the integral there. So we want to know if that's possible. So we're going to look at cases where a is negative infinity or b is positive infinity or both. The other type of improper integral is one in which you have a vertical asymptote somewhere within this interval from a to b. And just to be clear, right, it's not that f can't have discontinuities. It's fine. F can have certain discontinuities. It just can't have infinite ones, right? So for example, this function here, f of x is x plus 2 when x is less than 1, but x plus 3 when x is bigger than or equal to 1. That obviously has a discontinuity at x equals 1. But the integral from 0 to 5 of f of x dx is still well defined because you can just split it where the discontinuity occurs, and you have no issues with that. Okay. On the other hand, something like the integral from negative 1 to 1 of 1 over x dx presents more of an issue because you've got this infinite discontinuity that separates them. And you can maybe kind of argue that by symmetry that the integral should be 0 because these two areas should be equal and one of them is below the x-axis, the other is above. But we know from our work with limits that negative infinity plus positive infinity doesn't always equal 0. And then the other thing is that we don't actually know if these are infinite values because, again, this is getting really close to the y-axis. Maybe it kind of pinches it off. And so we end up with finite values here and here. And then imagine if you had, f of x equals x squared. That's in some ways even worse because now you've got these two things and they're definitely not going to cancel each other out. So like, does this approach some finite value or not? So these are the questions that we want to answer in this section. So let's get to it. Okay, so to answer the first question, right, here's how we deal with integrals where we have infinite intervals, okay? So let's say that b is positive infinity. The way we take care of that is that instead of writing this limit of integration up here as positive infinity, we'll just replace it with b, where we assume that b is some finite value. And then we'll evaluate the integral, and then take the limit as b goes to infinity. Okay, so that's how we'll take care of that case. Similarly, if a is negative infinity, well then we just replace that lower limit with the letter a, evaluate the integral, and then take the limit as a goes to negative infinity once we're done evaluating the integral. And then finally, if you have both cases, right, all you have to do is pick a convenient value where you can split the integral. And now this first half is like a case 2 type thing, and the second half is like a case 1 type thing. And so we know how to take care of both of those halves. Okay. Now, in each of these three cases, 1, 2, and 3, the integral is said to converge if the limit exists and it's finite. Okay. Otherwise, it's said to diverge. So let me walk you through a few examples. So let's evaluate the integral from 1 to positive infinity of dx over x cubed. Okay. So we're going to take care of this positive infinity in that upper limit of integration by replacing it with just the letter b, where we assume that b is some finite number. But then, and then we're going to, evaluate the integral, of course. But when we're done evaluating the integral, we'll take the limit as b goes to positive infinity, right? And that's all there is to that. This is a pretty easy integral to evaluate. 1 over x cubed is just x to the negative 3. So this is going to be limit as b goes to positive infinity of, it would be x to the negative 2 divided by negative 2, right? So negative 1/2 x to the negative 2 from 1 to b. Now we can plug in those limits of integration. We're going to get limit as b goes to positive infinity of b to the negative 2 would be 1 over b squared. I'm just going to write that as negative 1 over 2b squared. And then if we plug in 1, we're going to get just a negative 1/2. So I'm going to say minus negative 1/2. Okay. So now if we plug in positive infinity, this part's going to go to 0. And so we're just going to get a minus negative 1/2, so a positive 1/2. Okay, so this integral converges to 1/2, which is, again, kind of interesting. You've got this infinite interval over which you're integrating, and yet you end up with a finite value for that area. Let's look at another one, pretty similar to that one. Let's do integral from 1 to positive infinity of dx over x. Okay, so again, we're going to fix this up the same way. We'll take the limit as b goes to positive infinity of the integral from 1 to b of dx over x. That's going to be limit as b goes to positive infinity of ln of absolute value of x evaluated from 1 to b. We don't actually need the absolute values because b is positive and 1 is positive, of course. But this is going to come out to be limit as b goes to positive infinity of ln of b minus ln of 1. Well, ln of 1 is just 0, right? As b goes to positive infinity, ln of b is also going to go to positive infinity. So this ends up being positive infinity. Okay, so that's interesting, right? So this one converged to 1/2, but this one diverges, right? The integral diverges. It does not approach any particular finite value, right? It goes off to infinity, you might say. So that's kind of interesting. It would be, so in a second we'll look at, we'll come back to these kinds of problems, okay? For now, I want to look at the second type of improper integral that we looked at in the previous definition, one where you have negative infinity as your lower limit. So let's integrate from negative infinity to 0, 1 plus x times e to the x dx. Okay. Now, this thing, how are we going to integrate this? Well, first of all, let's take care of the limit, right? So this is going to be limit as a approaches negative infinity of the integral from a to 0 of 1 plus x e to the x dx. Okay, but now how do we evaluate this thing? It occurs to me that I could distribute the e to the x and get e to the x plus x times e to the x. If I do that, integral of e to the x is just e to the x. Integral of x times e to the x I think I would have to use differentiation by parts for that. But if I'm going to differentiate, or not differentiation, integration by parts. But if I'm going to integrate by parts, well, then I might as well just integrate by parts the way it's already written. So that's what I'm going to do. And actually, I'm going to use the tabular method for this because I know that I can just integrate e to the x all day long, right? It's just e to the x. And I can differentiate 1 plus x all day long. It's just going to go down to 0 pretty quickly. So let's do it. Okay, so this is going to go to 1 and then 0, right? It doesn't even take that long. That's going to be plus. That's going to be minus. Okay, so if I were just looking at the indefinite integral of 1 plus x e to the x dx, it would be 1 plus x e to the x minus e to the x plus c. If I distribute the e to the x now, this e to the x and that e to the x will cancel, and then I'll be left with an x e to the x plus c. Okay, so for the indefinite integral then, we'll have limit as a goes to negative infinity of integral from a to 0 of 1 plus x e to the x dx equals limit as a goes to negative infinity of x e to the x evaluated from a to 0. And then if we plug in those limits of integration, 0 times e to the 0 is just 0. So we get 0 minus a e to the a. Now we're going to take the limit as a goes to negative infinity. So a negative infinity will be a positive infinity. And then e to the negative infinity will be 0, right? So this is an infinity times 0 case, which is an indeterminate form, which tells you you've got to try to kind of fix that up somehow. Usually what we try to do is rewrite it in such a way that we can use L'Hopital's rule. Just to make it a little easier on ourselves, I'm going to do a little substitution and say let u be negative a, right? Now as a goes to negative infinity, negative a is going to go to positive infinity. So u is going to go to positive infinity. So this is equal to the limit as u goes to positive infinity. And then this negative a will be replaced with a u. And this positive a will be replaced with a negative u. The reason I kind of thought to write it that way is because now I can write it as u over e to the u, and that's a L'Hopital situation, right? Because this is infinity over infinity now, so you can just use L'Hopital. So this is, by L'Hopital, the limit as u goes to positive infinity. It's been a while since we've had to do limits, right? But it would be derivative of the top over derivative of the bottom. And that's much easier to compute now because if we let u go to infinity, this is going to go, the denominator is going to go to infinity, so the fraction is going to go to 0. All that work for 0. But there you go. This one I want to take a look at in Desmos real quick because I think it's interesting, right? So here we have 1 plus x times e to the x, and from negative infinity to 0, and we got 0. So what that tells me is that, notice that this part is above the x-axis, so this is a positive area. This part's below the x-axis, so it's a negative area. And so this must cancel that. So all of this kind of negative stuff that goes out to negative infinity is equal in area to this little bit, this almost triangular looking bit that's above the x-axis. So that's kind of an interesting fact. Right? Kind of an interesting example. But I want to come back to parts A and B because we have two very similar functions here. and yet one of them converged and one of them diverged. And I think a natural question to ask yourself at this point would be, well, for what exponents here is the result going to converge or diverge, right? So let's see if we can answer that question, and then we'll take a look at those graphs in Desmos as well. So for what values of p does the integral from 1 to positive infinity of dx over x to the p converge? Let's see if we can answer that question. Well, if p equals 1, then this is 1 over x dx, which is just ln of x, as we saw in part b of the previous example. But if p is any number other than 1, then the way we take care of this is we add 1, well actually we would call this x to the negative p, and then we would add 1 to the exponent and divide by the new exponent, right? So I'm going to say, so suppose that p is not 1, okay? Then the integral from 1 to positive infinity of dx over x to the p equals the integral from 1 to positive infinity of x to the negative p dx. That's going to be the limit as b goes to positive infinity of the integral from 1 to b of x to the negative p dx. So that's going to be limit as b goes to positive infinity of x to the negative p plus 1 divided by negative p plus 1, evaluated from 1 to b. Okay, so that's going to be limit as b goes to positive infinity of b to the 1 minus p over 1 minus p minus, if we plug in, well, if we plug in 1, we have issues, right? Because of the negative p plus 1 down there in the oh, I'm plugging it into x. I'm sorry. I don't know why I was confusing myself there for a second. But this would be 1 to the 1 minus p. Well, 1 to any power is just 1. So this is just going to be minus 1 over 1 minus p. So actually, I could just put that in here, right? Minus 1 over 1 minus p. Okay. Now we're going to take the limit as b goes to infinity. So the denominator is going to be fixed. As b goes to positive infinity, 1 minus b is going to go to negative infinity. B to the negative infinity. Maybe it would have been better to split that fraction. Hold on a second. Okay, sorry. I needed to get my bearings, and I keep confusing myself with the variables. B is going to positive infinity, not P, right? So I was plugging in positive infinity to P, but P is just a constant number. So here's how I'm going to approach this. So let me rewrite this as limit as b goes to positive infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p. Okay, so notice that if P, so we'll say if P is greater than 1, then 1 minus P is negative, right? And so you'll have b to a negative exponent. And so limit as b goes to positive infinity of b to the 1 minus p goes to 0, right? It would go to 0. Okay, because the exponent's negative, and so you're taking a really big number to a negative exponent. That's 1 over a really big number to a positive exponent, which is going to send it to 0. Okay? In which case, the limit this part would just go to 0, and so the limit would just be negative 1 over 1 minus p, right? And so the integral would converge. So limit as b goes to positive infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p would just equal negative 1 over 1 minus p, or if you like, you could call it 1 over p minus 1. So the integral converges. Okay, so we know that if p is greater than 1, the interval is going to converge, for sure. If p is less than 1, then 1 minus p is positive. And so the limit as b goes to positive infinity of b to the 1 minus p, well, this would be a really big number raised to a positive exponent. That's just going to go off to positive infinity. Right? So limit as b goes to positive infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p is going to equal positive infinity minus 1 over 1 minus p, which is just going to be positive infinity. So the integral diverges. Okay, and so there you have it, right? So if p is greater than 1, the integral converges. If p is less than 1, then the integral diverges. If p equals 1, as we saw in example 1 part b, the integral also diverges. And so we can say, therefore, the integral from 1 to positive infinity of dx over x to the p converges for p greater than 1 and diverges for p less than or equal to 1. Okay? And that's that one. So there's the answer, right? There's the answer to the question. So that's kind of an interesting thing. And I want to take you to Desmos now to kind of consider that a little bit. So let's look at 1 over x. So this would be when p equals 1. And then we'll look at 1 over x squared. This would be when p equals 2. And then we'll look at 1 over x cubed. So this is when p equals 3. Anyway, and we're really only interested in the integral from 1 to infinity. So 1 over x is this stuff in green, 1 over x squared is in purple, and 1 over x cubed is in black. So you'll notice that they all are kind of similarly shaped, but green diverges, but purple and black do not. In fact, let's give another one that doesn't converge, one that diverges. So it's if p is less than 1. So let's do like 1 over x to the 1/2 power, right? So this one also diverges, okay? So it's interesting, right? It's like these things they're all going to 0, but the red and the green, they don't go to 0 fast enough for the integral to converge. You still get like an infinitely large area. But the purple and black, they go down to 0 quick enough that it sort of pinches off the area, I guess you could say. So that's really kind of a fascinating thing in my opinion. But anyway, so that's that. Moving on now. I want to give you one more example before we move on to the next type of improper integral. And that is one of these where you have a negative infinity and a positive infinity together. So let's do one more example. Let's evaluate the integral from negative infinity to positive infinity of dx over 1 plus x squared. And you might think, well, we're going to integrate over the entire real numbers. How in the world are we going to get a finite value out of that? But just to kind of get our bearings a little bit, let's look at the function, right? It's 1 over 1 plus x squared. All right, so this is what the thing looks like. So you can see that as you go out to negative infinity, you're going to drop down to 0. As you go out to positive infinity, you're going to drop down to 0. So it's very possible that you could end up with a finite area there. So let's see if we do. So the way we fix these ones up is we split them. And I would say a good place to split this one would probably be 0. I mean, you could choose any number you like. I'm just going to choose 0. 1 might be a better choice. I don't know. It depends on what this thing's at. Actually, looking forward, I know that this is going to be a tangent inverse, right? And tangent inverse of 0 is just 0. So I think 0 is a good choice. But anyway, so I'm going to call this integral from negative infinity to 0 plus integral from 0 to infinity. And then you say, well, but you still have these infinite limits, but we know how to take care of these, right? Here we're just going to take limit as a goes to negative infinity of the integral from a to 0. And here we're going to take the limit as b goes to positive infinity of the integral from 0 to b. And that's really all there is to that. So, goodness. So we're going to have limit as a goes to negative infinity of tangent inverse of x evaluated from 0 to a plus limit as b goes to positive infinity of tangent inverse of x evaluated from from a to 0, and then here from 0 to b. Okay, so this is going to be limit as a goes to negative infinity of tangent inverse 0 minus tangent inverse a plus limit as b goes to positive infinity of tangent inverse of b minus tangent inverse of 0. Okay, now as I said, tangent inverse of 0 is just 0. So this is really limit as a goes to negative infinity of negative tangent inverse of a plus limit as b goes to positive infinity of tangent inverse b. Okay. And then from here, you just have to remember what the tangent inverse graph looks like. But I know that as b goes to positive infinity, tangent inverse of b is going to approach pi over 2. As a goes to negative infinity, tangent inverse of a is going to go to negative pi over 2. And so this is going to be a negative pi over 2 plus pi over 2. So that's just going to be pi. Easy as pie, right? That's really interesting, right? Like, how did this end up? How is the area of this thing equal to pi? Like, pi is the ratio of a circle's circumference to its diameter. Like how in the world are we getting that number out of this thing, which doesn't seem to be related at all? But nevertheless, right? That's the way that one worked out. So very interesting things can happen here. I want to move on to the second type now, though. So the second type of improper integral is one where you have an infinite discontinuity somewhere within your the interval over which you're integrating. So let's talk about how to deal with those, right? So if f has an infinite discontinuity at b, but it's otherwise continuous on the interval ab, then the integral from a to b of f of x dx is just going to be limit as k approaches b from the left of the integral from a to k of f of x dx. Now, this from the left business might have you scratching your head a little bit. Basically, we're saying if it has like a vertical asymptote at the endpoint here, b, right? That's basically the situation. And so you get a picture that looks kind of like this. And so you're just going to let b be some number k, but then you're going to let k approach b. So maybe k is like right here or something. But then you're going to let k approach b from the left-hand side, right? So k is going to get closer and closer to b from the left-hand side. And then that should yield the same result, right? So then similarly, if you've got a vertical asymptote on the left endpoint a, well then you're just going to take this, replace a with k, and then take the limit as k approaches a from the right, right? You're going to approach a from the right. And then finally, if f has some kind of infinite discontinuity within the interval somewhere, but it's otherwise continuous everywhere else on the integral, or on the interval, then you're just going to split the integral at c. And of course, then you're going to have a right endpoint with a vertical asymptote here and a left endpoint with a vertical asymptote there. But you know how to deal with those because this is just a case 2 and this is just a case 1 situation. Okay. And again, you know, the integral is said to converge if the limit exists or if the limits exist, like in the case of case 3. And then the integral is said to diverge otherwise. So let me walk you through a few more examples. So 3 more examples. So let's evaluate some of these things. Okay, let's evaluate integral from 0 to 1 of dx over square root of 1 minus x. So notice that here we have a vertical asymptote at 1, right? Because 1 makes the denominator of this fraction 0. So we've got a a right endpoint where we have this infinite discontinuity. So we fix that up by saying this equals limit as k approaches 1 from the left, right, of integral from 0 to k of dx over square root 1 minus x. Okay, now if I were to do a u substitution here, I would let u equal 1 minus x, and then du would be negative dx. So I can just hand myself a negative dx here if I put a negative sign out there. And this would just turn into 1 over square root of u, which would be u to the negative 1/2 power. So let me see if I can do this without having to actually do the u substitution, but I think I can do it. Okay, so it's going to be limit as k approaches 1 from the left of negative u to the negative 1/2. That would be u to the positive 1/2 divided by 1/2, so 2u to the 1/2. Or 2x, since I didn't actually make the replacement. Oh, not x, 1 minus x. 2 times 1 minus x to the positive 1/2. Or I guess we could just say square root, but whatever. Evaluated from 0 to k. So I think that'll work. Going the other way around is always easier. If I differentiate this, I'm going to have 1/2 times negative 2. 1/2 times negative 2 is negative 1. So it's going to be negative 1 times 1 minus x to the negative 1/2 times negative 1. The negative will cancel and give me what I had originally. So yes, so we're good. Okay. So if I plug in k now, I'm going to have negative 2 times the square root of k minus x. If I plug in, 1 minus k. I keep doing this. I don't know what my problem is. 1 minus k. I'm plugging in for x, right? 1 minus k. Square root of 1 minus k. If I plug in 0, 1 minus 0 is 1. Square root of 1 is 1. 1 times negative 2 is negative 2. So I'm going to get minus a negative 2. Okay, so now as I approach 1 from the left, well, if I just plug in 1, I get square root of 1 minus 1, which is 0. So that's fine, right? So I would just get 2. I would just get 2. So this thing equals 2. Kind of interesting. Okay, so there's that one. Here's another one. Let's do integral from 1 to 2 of dx over 1 minus x. Okay, so a very similar thing to what we just saw a second ago. But notice that this time the infinite discontinuity is on our left endpoint, 1. So, but we handle this the same way. We're going to say that this equals limit as k approaches 1. This time we're going to approach 1 from the right. And it's going to be integral from k to 2 of dx over 1 minus x. So kind of jumping forward, this is going to be limit as k approaches 1 from the right. I think we're going to get negative ln of absolute value of 1 minus x, I believe. If we differentiate, we would get negative 1 over 1 minus x times negative 1. The negatives would cancel. So that looks correct. If I plug in 2, 1 minus 2 is negative 1, but absolute value of negative 1 is positive 1. ln of 1 is 0. So if I plug in 2, I get 0. So limit as k approaches 1 from the right of 0 minus, if I plug in k, I'm going to have ln of, minus negative ln of absolute value of 1 minus k. So if I'm approaching 1 from the right, then that means k is going to be slightly bigger than 1. Not that it matters because I'm going to be taking the absolute value anyway. But if I just plug in 1, I suppose, I would get ln of 0. That is kind of a problem, right? But ln looks like this, right? And it crosses the x-axis, at 1. So ln of so limit as we approach. I'm confusing myself. Hold on. We're approaching 1 from the right. So ln of 1 minus k. Oh goodness, that would be negative k plus 1. So we've flipped it and shifted it up 1 unit. Not 1. Not up. Sorry. We flipped it and we've shifted it left 1 unit. Goodness gracious, why is this so hard? Why is this being so difficult for me? Anyway, we would get something that looks kind of like that. Okay, where this is like negative 1, right? So no, that's still not right. Goodness gracious. Why is this giving me such trouble? As we approach 1 from the right, we're going to be approaching ln of 0 from the right. It's going to go to negative infinity. It's going to definitely go to negative infinity. So this is going to be negative infinity. Anyway, the moral of the story, though, is that it diverges. So the integral diverges. I think my brain is too tired. It's been a long week. But yeah, the interval diverges there. Let me give you one more example, and then we'll call it a day. I need to take a break. Let's do integral from 1 to 4 of dx over x minus 2 to the 2/3 power. Okay. So this time we're going to have vertical asymptote at 2. And 2 is right in the middle of this interval. So we're going to have to split the integral at 2 and say, okay, so this is the integral from 1 to 2 of dx over x minus 2 to the 2/3 plus the integral from 2 to 4 of dx over x minus 2 to the 2/3. And then we can replace 2 with k, and here we'll take the limit as k approaches 2 from the left. Of the integral from 1 to k. And here I'm just going to call this x minus 2 to the negative 2/3 dx. And then here we'll take limit as k approaches 2 from the right of the integral from k to 4 of x minus 2 to the negative 2/3 dx. Okay. So this is going to be limit as k approaches 2 from the left of x minus 2 to the 1/3 divided by 1/3, so it would be 3 times x minus 2 to the 1/3. So 3 times the cube root of x minus 2, I suppose. So 3 times x minus 2 to the 1/3 evaluated from 1 to k, plus limit as k approaches 2 from the right of same thing, right? You add 1 to the exponent, you get 1/3, divide by the new exponent, and that's the same thing as multiplying by 3. So 3 times x minus 2 to the 1/3 evaluated from k to 4. Okay, so now if we plug in k, we're going to get 3 times k minus 2 to the 1/3. If we plug in 1, 1 minus 2 is negative 1. Cube root of negative 1 is negative 1. Negative 1 times 3 is negative 3. So we're going to be subtracting a negative 3. That's the same thing as adding 3, right? Okay. Here we're going to get limit as k approaches 2 from the right of, if I plug in 4, 4 minus 2 is 4 minus 2 is 2, 2 to the 1/3, cube root of 2 is just, well, cube root of 2. So it'll be 3 times the cube root of 2. And then if I plug in k, I'm going to have minus 3 times k minus 2 to the 1/3. All right, let's see if we can evaluate these limits now. This is the part that's been giving me trouble all day long. But if we plug in 2 for k here, that's just going to be 0. So we're just going to get 3. If we plug in 2 here, again, that's just going to be 0. We're going to get plus 3 times the cube root of 2. And that's that. So that one actually didn't end up being too bad in terms of evaluating the limit. But I did want to say one more thing before I call it a day. And what I wanted to say was that it may seem silly to go through all these, like, it may seem like extra steps or something. But it's not, because if you ignored the fact that there's this discontinuity at 2, and you just went, you know, integral from 1 to 4 dx over x minus 2 to the 2/3, and then you just evaluated this integral, right? And you got 3 times x minus 2 to the 1/3 evaluated from 1 to 4. Then you would be misled, right? Because you would think, okay, so this is going to be 4 minus 2 is 2, so you get 3 times cube root 2. And then if you plug in 1, then you get 1 minus 2 is negative 1, cube root negative 1 times 3 is negative 3. So you would get this. You would get this, right? Which is a very different outcome. They're obviously not the same number, right? So, so this one, of course, is wrong, okay? And the reason it's wrong is because you're missing the fact that you've got this discontinuity you've got to take into account. And so this is why it's important to apply these definitions, right, when you're working on these kinds of problems. Okay, so that's all I have to say about 7.8.